Dave out in Western Pennsylvania, and I'm a chemistry professor and with the University of Pittsburgh's Bradford campus. And in this third installation of Diels Alder, this would be video number 6, the virtual organic lab. And this program, the virtual organic lab, is sold by the Beyond Lab Z, and it was developed originally by chemistry professors at Brigham Young University about 2002. I recall reviewing it at that time. It's an excellent program, $25 a year annual license for a student in the United States, and the tech service is also excellent, so I recommend it. And I'm using this right now for remote education in the Organic One lab because we can only deliver courses via remote education because of the pandemic. In this third installation, I want to do the certain Diels Alder, and I want to come over here and grab the quinone. I want that one. Cyclopentadiene as the conjugated diene. I'll put it in nonpolar solvent, diethyl ether. Certainly not ethanol or water. I think we want nonpolar there. And there are the 3 components: diethyl ether, quinone, and the paraquinone, and the cyclopentadiene. We bring that over to the hot plate, attach the heating mantle, the stir plate, reflux condenser, nitrogen gas. We're ready to go. Note the clock. If you haven't looked at the earlier videos, you can maintain a notebook. Here, I'll do the initial thin layer chromatography, and that's the mixture showing right there. We could save it into the notebook, and I'll try that right here. And then I'll click OK, open up the notebook, and the TLC is there. You can record your name, the date, the time. You can adjust the time in the lab to whatever time you want. I would just say, well, I'm starting at 7:11 p.m. in the virtual lab. Okay, let's get underway by clicking stir. And they use specific rate constants for these reactions, so it would dovetail with what you would normally expect. Some reactions have to be heated for an hour, some more than that. Some would be conducted at ambient temperature. Some would be carried out in an ice bath. I'm going to move this up an hour. See, right now we have those 3 components. I'll move up an hour, and you can see the product is forming. There's the monoadduct. They will only show you the monoadduct. They don't show you the diadduct. So you're reacting 1 mole of each of the starting materials. And I'm going to go up another hour. If you move too fast, the glass could explode. And that's why you don't want to fly too fast through this. Now look, the reaction's done. Do you see that? No starting material. We can do a TLC there, and it would be slightly different. It's a little lower than the starting material. Do you see that? I'm not going to save that. Now, the product, if you've done your homework and you look up the melting point, in this case it's a solid of the product, you just want to rotovap off the diethyl ether. Now, the way you can do that in this third approach to work up, I did this in the last 2 videos. I looked at different pathways. You can move that right to the crystallizing dish. Oh no, they won't let me. So, SEP funnel, doesn't hurt to wash it. Lower layer water, see there's nothing else in there, but we couldn't be sure. Top layer is what we want. Now see, it's diethyl ether in the product. So what we presume to do, we take that top layer, go to the evaporating dish, crystallizing dish, and we would allow that to evaporate. The diethyl ether has evaporated, presumably in the hood. You see that yellow solid? Now, we can do an infrared of that. Okay. We can do a proton NMR. Okay. We can change this to C13 and get the signals. There's your carbonyl down around 200, which I mentioned in a prior video. And we can do a melting point. Now watch how this is done. Oh, mass spec. fragmentation pattern. And the molecular ion is the base peak as well. That happens once in a while, not all the time by any means, but here it does. And then melting point. Now, this is how we do this. Bring that over. 77 degrees. That's when this compound melts when it's pure. And I would have students look that up and verify that that would be the melting point. A very, very good database is the SDBS online. Go to Google and type in SDBS. It's put out by Japanese Analytical Society, and it's excellent. I use it with my students to look up infrareds, NMRs, mass spec, and I would have students learn to use the scientific literature, electronic journals, Google patents. I introduced them to how to maintain a research notebook. And the SDBS, it's very good to get them started. And I also point out the Sigma Aldrich catalog, let's say, or Acros, for purchasing chemicals for bench scale studies. Hey, thanks for watching. Bye for now.